Alright, here we go. So what we got right here, we have the first of our three AP level packets with all the tough problems in them. This one's on kinematics. The text is a little bit small, so I'll do my best to zoom in and zoom out and focus. But ideally, you, the viewer, would have one of these already printed out so that you can follow along at home. Alright, then I'll read every single question right off the bat. Well, I'm not doing every question, right? Because nobody sent me any suggestions, so I'm just doing my favorite ones. Alright, I'm picking the ones that I feel like solving. So here we go. Alright, actually I'll just do the ones that I got the most questions about. Alright, so number one, car travels 30 miles at an average speed of 60 miles per hour, and then 30 miles at an average speed of 30 miles per hour. The average speed of the car over the 60 miles is blank. Alright, so some people, they see the 60 miles per hour, and then they see the 30 miles per hour. Alright, so first it goes at 60, then it goes at 30. Obviously, the average must be in between, and then they go to circle 45. Right? Wrong. Alright, that's not the answer. It's not that simple. It's not just in between. It is a simple process, but it's not. It's kind of physics related, but it's a little bit of thinking outside the box. Alright? So, if our first car, well, actually, you know what? Before I even do this, let me just write an equation up here, right? We want our average speed, right? Average velocity. Well, what's that? It's just a measure of distance over time, right? But if we have two segments in this whole trip here, if we have two segments of motion, right? First we're going fast and then we're going slow. Both of those still get taken into account, right? We want the total distance, the distance from the first segment, and the distance from the second segment when it's traveling slower. So really you could also look at this as d1 plus d2 over t1 plus t2. Almost did. Mixed up my t's and pluses, right? So our first distance is 30 miles. It goes 30 miles at 60 miles per hour, then 30 miles at 30 miles per hour. Well, in both cases, it's going 30 miles, right? 30 plus 30, obviously, this is going to be 60 miles up here. And then we need to know our total time. So if it goes 30 miles at an average speed of 60 miles per hour, then it should be able to do that in half an hour, right? I mean, I could write the equation out for that, but you're all smart enough to understand that already, right? Of course. So then the first time is half an hour, right? It takes half an hour to go 30 miles at 60 miles per hour. Then it goes another 30 miles at 30 miles per hour. So that would be a whole hour. So 0.5 plus 1. So this is basically 60 divided by 1.5. Right? We plug that into our calculator, 60 divided by 1.5, and we get 40. Well, that came out to be a nice even answer. So that's your answer, 40, not 45. Why is it 40 though? It's for these types of problems you can, the answer is not always that obvious, but sometimes you can eliminate everything but one answer. Doesn't necessarily work for this question, but if it goes at 60 miles per hour, then it travels at 30 miles per hour. And if it's going the same distance, it would take longer to go the same distance at the slower speed, right? At 30 miles per hour. It spends more time traveling at the slower velocity. So if you're taking the average of the entire trip, but it spent more time traveling at the lower velocity, obviously your average is going to be closer to the lower velocity, right? It's not going to be smack in the middle, it's going to be closer to the lower one. And well, this time they also included 35, right? But sometimes, you know, you do have enough information to determine right off the bat what the answer should be. But if that's not the case, then you can just remember these nice simple steps. Okay? Questions 2 and 4, or 2 through 4, they use these two graphs, right? For particle A and particle B, particles moving in one dimension. Sounds very scientific, but it's very simple. You don't need to worry about how are these two particles existing and traveling on their own. Right? All we care about is the motion and the data. So one of them, right, these are velocity time graphs. Right? Velocity time graphs for two different objects traveling two different speeds, right, but it's the same type of graph. So I would definitely review kinematics graphs. What's the significance of all the pieces of the graph, all the points on the graph, right? What does it mean that our curve is up here, right? And what does it mean when it goes underneath your x-axis? Right? Well, obviously, we start off with a positive velocity for the first particle. Right? We're traveling at a nice positive velocity, constant velocity, right? Because within that first second, our velocity hasn't changed, right? It stays at 1 meters per second, it stays straight. Doesn't increase, doesn't decrease. And then immediately at 1 second, now we have a very quick change to negative 1 meters per second for a total of 1 second. Okay? So you could do the math. You could try to read the graph, get all the data, and plug that into your kinematic equations, but honestly that's really boring. And you're also, on the actual AP exam, you're going to be pressed for time. Right? You don't have that long to spend on all these questions. You can't really sit down and start doing equations for every single graph that you see. Right? So that's not what they're testing here. They're testing, do you understand what does the shape of the graph mean? Right? Without using your equations. Which particle is the furthest from the origin at 2 seconds? Right? Well, this one, first it has a positive velocity, then it has a constant negative velocity. This one is increasing. We have an increasing positive velocity the entire time. Right? So this one is always traveling forwards. It's always going forwards. This one travels forwards for 1 second, then it travels backwards for 1 second at the same speed in the opposite direction. Right? So knowing that, that should be enough information to tell you that particle A is back where it started. Particle A is back where it started, but that's not what they're asking. They're asking you which one is the furthest. Right? So A is back where it started, so that means that B has to be the furthest one. Right? B has not a constant velocity, but our velocity is always positive. It's always going forward. It never backtracks. Particle A ends up back where it starts, right? So it can't be the furthest one. The other thing to remember, right, the area under the curve means different things on different graphs. On an acceleration versus time graph, that would be your change in velocity, but here this is your change in distance, right? And our change in distance above the x-axis, this tells us how, if you were to calculate the area of that, right, well basically it's just 1 times 1, right? It travels at 1 meters per second for 1 second, it'll travel 1 meter. But if you look at it geometrically, right, the areas represent the distance that this object has traveled. So we have two equal areas. One of it's above the x-axis, the other one's underneath. So this tells you that it's going forwards, and now we just created the same area underneath the graph. So that's telling you it's basically canceling out the amount of distance that's already gone. Okay? And then for this question, or for this graph, right, we don't have any nice simple geometry equations to calculate that, right? But the distance at the end of 2 seconds would be equal, it would be the same as this area underneath that curve. Which particle moves a constant non-zero acceleration? Alright, this one, the wording is very important. Don't get tricked. Alright, read the problem carefully. Which particle moves with constant non-zero acceleration? Right? So we need to have, doesn't tell us whether it has to be positive or negative, right? We just need to have constant acceleration that's not zero. Well, if we look at particle A, right, our velocity is unchanged, right? You have a constant velocity and then an instantaneous change to a negative velocity. So that technically, they don't count that as acceleration. It's just two separate segments, right? Just a constant velocity and then another constant velocity in the opposite direction. Alright, so it can't be A. A is always going at constant velocity, right? That's not the same thing as constant acceleration. That's zero acceleration. Particle B, Okay. I mean, this question has gotten me before, right? I've had to sit down and think about this one for a little bit. But particle B, right? It looks like it's accelerating, right? Well, it definitely is accelerating because our velocity is increasing, right? But the key word here is we want a constant acceleration, right? And on a velocity time graph, your slope, the slope of the graph represents your acceleration. Do we have a constant slope here? No, we don't. We have an increasing slope. So this would be caused by an object with an increasing acceleration. All right, so it can't be A, it can't be B. Our correct answer is neither A or B. Right? And then question number 4, which particle is in its initial position at 2 seconds? Well, we pretty much already answered that, right? It has to be A. It goes a distance of 1 meter in the positive direction, then it turns around and goes 1 meter back in the negative direction. Right? So it just goes back where it started. So that would be particle A. Okay? Okay. Actually, alright, so question number 5, different graph, but they're almost kind of asking the same thing. The graph above shows the velocity versus time for an object moving in a straight line. At what time after t is equal to 0, right, does the object again pass through its initial position? So because this is a velocity versus time graph, right, the answer is not just when it crosses our x-axis. Right, that's not the answer. If this were a distance versus time graph, right, then it'd be going back to its starting position, right? But that's not the case. This is velocity versus time. So all this tells us is that we're increasing our velocity in the negative direction, slowing down in the negative direction, and then now we are increasing our velocity in the positive direction, right? But that only tells us how our velocity is changing. It doesn't tell us what the displacement is. Where is its position, right? Well, in order to get displacement, it's the same trick that we used on the last question, right? The area underneath the curve for a velocity time graph gives you displacement, right? So here at the beginning we have a negative displacement, right? Now we start going back. In order to get back to the origin, we need to have the same amount of positive area on top. Alright? So there's no way to calculate perfectly where it would happen, but that's okay. Right? Some of these questions aren't asking for an exact answer, they're just asking you for a range. And it definitely can't be before 1 second, right? Because it's after here that we start generating positive area, right? We need enough area to cancel this out here. So you can't really calculate it, but you can eyeball it, and it definitely happens before you get to 2. Alright? So it would be between 1 and 2 seconds. Doesn't happen at 1 second, right? Definitely wouldn't be between 2 and 3. The only way you could possibly be confused if you're deciding does it happen between 1 and 2 or exactly at 2. If you really look at it, if we filled it in all the way, alright, that's definitely way too much area on top, right? So it's in between 1 and 2. Alright, so that's how we answer that question. Alright, I'm going to continue with the graphing theme. I'm going to skip 6 and go straight down to number 7. Actually, this one's kind of an easy question. Right, if this is position versus time, or displacement versus time, the displacement x of an object moving along the x-axis is shown above as a function of time t. The acceleration of this object must be, on a distance versus time or displacement versus time graph, your slope means velocity, right? Slope represents velocity. Change in distance over change in time, right? Change in x over, or change in y over change in x. So we have a constant slope, so that means we have a constant velocity. So if you have constant velocity, you can't have any acceleration. So that means the acceleration must be 0. Right? So I think I'll pause it right here, and I'll do another video for the next page.